Hello guys, my name is Ravi. Today I am going to explain about reversible logic gates, one of the trending concept in this era. Here I am going to explain about parity preserving reversible QCA gates, that is also called as PPRG, which uses the concept of reversible logic gates. And let's get started with this. And first, as a first part, I would like to say these are my contents, that is introduction, review, and functionality of PPRG, then realization of full adder, then fault detection and isolation methods of PPRG. Then in the first part I have the introduction thing. As we know that heat dissipation is one of the limiting factor in any complex digital circuit designs. Randall Lander proved that for every bit erase of information, Ketiland 2 joules of energy is lost. That means information loss is nothing but energy loss. Then this would not occur if computation is carried out in a reversible way. A reversible computation does not require any bit of erase of information. Consequently, no dissipation, no power dissipation in that manner, you can say, as I said before. Then reversible computation includes QCAs achieving less than KT-LAN2 switching energy dissipation. QCA techniques are used to design PPRGs. QCAs offers high device density, low power consumption, and high switching speed features. Then moving on to review of QCA and reversible gates. Review on QCAs, and first part is QCA cell. In this we can see that there are two different logic states, that is logic 0 and logic 1, depending on the position of electron. Electrons are the major important factor in QCA cells. Depending on the positions of these electrons, that is in which diagonal places they are placed, they are defined as logic 0 and logic 1 states. Then how does that signal propagation can occur using these QCA cells? As you can see here, it is unpolarized, and then it is polarized due to Coulombic force because of the adjacent polarized QCA cell that is in the logic 1 state, and it is forced to logic 1 state, and logic 1 will propagate like this, you can say, and forming a QCA wire. Then moving on to QCA clocking schemes, we have 4 different phases of clocking. We have, that is, first one is called as switching phase, where initially it gets polarized into one of its states like logic 1 or logic 0, and hold phase where it is maintains its polarized state as logic 0 or logic 1. Then it starts you can say like it starts degrading its polarized states and moves on to relax phase where it completely loses its clocking strength, that is, in the sense we can say like polarized state is lost and it is in the relaxed phase. Then we go to cross-sectional view. We have 2 things to be kept in mind, that is metal conductors and silicon substrate is placed and QCA cell is sandwiched in between them. If I apply a clock in the Y direction, electric field is produced in Z direction, as we know from thumb rule. That will happen here also, and signal will propagate in the Y direction. Then moving on to basic logic gates of QCA, that is first one is an inverter. Then we have 3 input majority gates. This is one of the important basic gates in QCAs, where 3 input majority gates is used to design AND gates and OR gates. If I have fixed this A pin as 0, I will get an AND gate. If I fix that A pin as 1, I will get OR gate. Then moving on to review on reversible gates, we have the definition here. A gate or a circuit that does not lose any information is known as reversible gates, or you can say like which generates unique outputs for each input vector. it is also a reversible gate, and number of inputs should be equal to number of output, that is 1-to-1 mapping should be there between input and output. That is one of the main basic criteria for designing any reversible gates. Then moving on to some popular reversible gates, we have first one as Fredkin gate, Toffoli gate, and Pieris gate, and QCA gates. Then moving on to other gates, like there are gates like RUG gates, RM gates, and CQCA gates and TQCA gates. Then moving on to the operation of Toffoli gate, we have Toffoli gate defined in this manner. For inputs as ABC, we have outputs as PQR, which is equal to P is equal to A, Q is equal to B, and R is equal to AB XOR C. Here, as you can see here, pins A and B are called as control inputs, and if I say that I got the output as 1, which means P is equal to A corresponds to A should be equal to 1. Then if I got Q as 1, that means B should be 1. So if I got R also as 1, then C should be 0. That you can make out from this truth table. Hence, from a given set of outputs, I can able to predict the input. That is one of the basic thing which we can observe from reversible logic gates, and it is one of the best feature we can say in reversible gates. Then moving on to the next part, that is functionality of PPRG. We have first thing, that is PPRG design, where we have the schematic diagram which looks like this. For designing PPRG, we require one XOR gate, 2 NOT gates, and 2 muxes, that is 2:1 mux. And the output pins are defined as P is equal to A XOR of B, Q is equal to AC plus B dash C dash, and R is equal to A dash C plus B dash C dash, and truth table is shown here. Then moving on to its layout, can be seen like this, and also its simulation results are shown here. As you can see here, the outputs are obtained after 1 clock cycle, that is after 4 clock phases. That is the important characteristics of PPRG. And why it is called as PPRG, that is parity preserving reversible gates? Because we can see from here that the parity is preserved between input and output for any sort of input vector. That is, if we have 0, 0, 0 as input set, then output is 0, 1, 1. Then moving on to the next slide, that is PPRG 2DW gate. Here we are seeing the clocking schemes for this and its corresponding layouts. And then moving on to the next part, that is, here we have listed a gate counts comparison for 13 standard functions like f is equal to ABC, f is equal to AB, and f is equal to ABC plus ABC, and so on, for different reversible gates like CQCA, TQCA, and Toffoli gates, and so on. As you can see from the last column, that is, PPRG has got the least quantum count, that is 25 here, as shown here. And then that is one of the improvement we can see here. And then moving on to cost comparison of PPRG, we have the comparison between Fredkin gate and PPRG. As you can see from this last row, that is, improvement has been seen in terms of gates and quantum count and area also. And moving on to the next part, that is leakage and switching energy dissipation results. As you can see from here, the leakage and switching energy dissipation is plotted for three different EKs, that is 0.5 EK and 1 EK and 1.5 EK. As you can see, PPRG and PPRG2 DW gates have got minimum energy dissipation. Then moving on to power dissipation mapping. Here there is a comparison you can see between PPRG and PPRG2 DW. As you can see that PPRG2 DW has got maximum power dissipation because it is using a clocking scheme. That's the reason. Then moving on to realization of fault-tolerant full adder. Proposed reversible full adder. Here, schematic and its simulation results are shown here. In building a full adder, we have used 3 PPRG gates, and one of the basic characteristics of this PPRG can be seen here, that is fan out is allowed in this QCS, which are not allowed in reversible gates because it is using a quasi clocking scheme. Hence we can use fan out characteristics here. Then moving on to the next part, that is comparison of fault tolerant full adder designs. It is compared with respect to Fredkin, Toffoli gates and QCA1 and RUG gates. As you can see, overall cost is calculated by using this formula, that is N of mg square, that is N of mg means number of majority gates and N of inverter means number of inverters and C means number of crossovers and T means delay and N of RG means number of utilized reversible gates. And as you can see that PPRG has got better improvement features in terms of overall cost, cell count and area. Then moving on to the last part, that is fault detection and isolation methodology. And in this thing, before starting with that, different PPRG arrangements I am going to explain now. That is, first one is completely cascaded PPRG based design arrangement, where we don't have any what you can say like pre pins. All pins are used, that is all three outputs are used as an input for the succeeding PPRG gates. Then one more arrangement is partially cascaded PPRG, where we will be having a few you can say like unused pins, and muxes are used for realizing this thing, and the select pin is called as fault flag pin. Then moving on to lookup table and fault mapping table. These two tables are most important in for the design, or you can say like for the models which we build. Here as you can see, this is the lookup table which we are using for staggered fault mapping lookup table for PPRG. It is used for PPRG fault analysis. As you can see, for example, if I take test input as 111 and expected output is 010, but the faulty output is 110. By comparing in terms of parity of input is 0 here, and parity of output we got it to be 1. Hence we can say like it is staggered fault 0, and you can say like from this lookup table that fault pin is B. And moving on to the fault mapping table. Here if I take an example like primary input is A0, that is 000, then it will be obtained at level 4 output, that is if it is obtained at 4th PPRG gate, then this table is used for completely cascaded designs, and this table is used in terms of matrix, and it will be helpful for uh, saying the algorithm, as we will see in few minutes. Then we want to cascade PPRG design. We have fault-free design and faulty design. As you can see from here, if in the fault-free design, if the inputs are 0, 0, 0, that is A naught, then a selection matrix is used and test array is obtained from that. Test array in the sense the input vectors like A naught, A3, A5 and A6, as you can see from this fault-free design. And moving on to the next step, that is we need to define three variables, that is design length, which is equal to 5. Design length is nothing but how many PPRGs which we are using, that is equal to 5 here, and F1, which is equal to design length divided by length of test array. Length of test array is 4, so F1 will be equal to 1, and F2 is also equal to 1 because F2 is defined as design length mod of length of test array. Then moving on to the next step, that is if the main output which we have obtained, that is if it is equal to A4, that is 100, as you can see from faulty design thing, which is not equal to test array of 1, that is 011. Here parity is not matching, hence fault is detected and error isolation procedure will start. In the error isolation procedure, we will look into each section and we will proceed further. And as you can see from this output at section 0 is 011. If it is not equal to primary input, that is 000, it is not matching in terms of parity again, and error has been detected in section 0, that is parity of PPRG of 3 is equal to 1, but which is not matching with parity of primary input, that is equal to 0. Hence error has been detected in PPRG 3 in section 0. That is the logic which they have used. And then move on to the next slide. The last part is partially cascaded PPRG based design. We have muxes which are used here. As I told before, muxes are used for designing partial cascade PPRGs. And if we have fault flag as 0, it indicates that it is used in fault free state. If fault flag is set to 1, we will say that it is having some fault in the design. And this circuit is designed for getting the function as f7, which is equal to a dash bc plus abc whole dash plus abc dash. If any same procedure is followed as before, that is completely cascaded thing, but the thing is it will get converted to completely cascaded arrangement only when faulty flag is set to 1. That is the main thing, and same error detection and error correction procedure as defined before is used here also. Then move on to the last part, that is conclusion. Here we have seen that complex logic realization is possible with PPRGs with high Boolean expressiveness, and average gate count is also least here, and cascadability is better, and the design occupies less area, and larger QCA robust reversible circuits can be designed, and fault detection and isolation methodologies are proposed, which can be used and can be extended for operations like syndrome based error correction operations. And these are my references. Thank you.